Thank you for the invitation. So in this talk, I will mainly focus on the constant in the log Sobolev inequalities, especially want to study how the constant depends on the geometry of the underlying space. And moreover, our target is for the dimension independence property of this constant. The space we are looking at here are homogeneous spaces equipped with a natural sub-Riemannian structure. Later in the talk, I will also give some applications of this dimension independence result, and I will provide some examples. Even though in this talk and in our paper, we only focus on sub-Riemannian spaces, actually, this method provides a general framework to study log Sobolev inequalities and other functional inequalities in a setting where no well-defined curvature bounds are available. And sub-Riemannian manifolds are just one of those examples. And hopefully, we can extend this tool to other more general settings. This talk is based on these two papers with Masha. And actually, the idea of this talk is these two papers are motivated by a paper of Gross in 1991, where he studied such inequalities in the Riemannian setting. Here is the outline of my talk. I will first recall some basics about log Sobolev inequalities on Rn, and then I'll move on to our setting, that is the homogeneous spaces with sub-Riemannian structures, and look at the hypoelliptic log Sobolev inequalities there. After that, I will provide some concrete examples. Some of them you have already seen in Marsha's talk. If time allows, in the end, I will also describe some further directions. So first, let's recall the log Sobolev inequality on Rm. This is first introduced by Gross in 1975. So on Rn, if we take a Gaussian measure, this is a probability measure, and it has a nice smooth density with respect to the Langbing measure as our reference measure. Here we have the Gaussian density. But from another perspective, this is the heat kernel at the time t equals 1 for the Laplacian on Rn. Then we have the following inequality. The entropy can be bounded by a constant capital C times the facial information. What's special about the constant is that it is independent of the dimension n. Here, the version of the inequality I present here is the classic one that with respect to the Gaussian measure. But actually, we have a more general version of the log Sobolev inequality in terms of the Markov semigroup, as we have already seen in Marsha's talk. So in that version, you can write the Markov semigroup as the integral of some function times the heat kernel measure. And the heat kernel measure in that case, Rn, it has the density with respect to the Lebesgue measure as the heat kernel. So that's why it's called the heat kernel measure. And on Rn, the only change you have to make in the Markov semigroup version for this functional inequality is that the constant is the capital C in our version times the time t. So here the constant there will be linear in the time t. And this linear growth comes from the space scaling of Rn and the scaling property of the heat kernel and the heat semigroup. But throughout this talk, I think I will stick to the classical version of log Sobolev inequality written in terms of an integral with respect to some measure. Before I move on, let me briefly discuss some applications of this dimension-free property. First, it has some important applications in quantum field theory. That is actually the origin where this problem coming from. In the quantized model, which has infinite dimensional spaces, it's important to have something with dimension-free constant. And actually, the consideration of the Gaussian measure in the first log Sobolev inequality comes from the study of Gaussian measure in the infinite dimensional spaces, where in that setting, you don't have a natural Lebesgue measure as your reference measure. So Gaussian measure is a very natural choice. And also, in that case, there is no Sobolev inequality available, and log Sobolev is the best you can hope for. Second, this inequality is equivalent to the hypercontractivity property of the Markov semigroup. This is proven in the celebrated paper in Gross of Gross in 1975. Third, proving a log Sobolev inequality can give you the convergence of this Markov semigroup to the equilibrium as time goes to infinity. So this is very useful in the study of some diffusion models, while to directly study its asymptotic behavior can be quite complicated, but proving an inequality, it automatically would give you this convergence to equilibrium. So the first three applications are more from a Markov semigroup perspective. The fourth one in geometry, it's more related to the entropy property given by log Sobolev inequality. That is, log Sobolev inequality can give you the entropy decay, actually exponential entropy decay. And this is closely related to the monotonicity formula in geometric analysis. So for example, we have the Perelman's monotonicity formula for entropy in Ricci flow. And in Minkowitz flow, you also have the Huysken's monotonicity formula. And this can be studied using the log Sobolev inequality. And actually, the consideration of Gaussian measure, it also seems to be quite natural in this setting. For example, the log Sobolev inequality with respect to the Gaussian measure, this is closely connected to the Gaussian type isoparametric inequality. But actually, the minimizer for the Gaussian area, the critical point for Gaussian area, it's the self-shrinker in the Minkowitz flow. So this will have some, this study of log Sobolev inequality would provide some interesting tool in that direction as well. Then, as we've seen, the log Sobolev inequality can also imply the concentration phenomenon of measures, where you view those functions that satisfies the log Sobolev inequality as the density of some measure, a class of measure, which take the Gaussian measure as the reference measure. And this concentration phenomenon, it's quite studied quite a lot and used a lot in random matrix theories. Last but not least, as mentioned by Masha, we have some nice connection to the optimal transport direction. For example, log Sobolev inequality can imply some transportation cost inequality, and it's very interesting. And also, some results in this direction have been also quite explained in the work of Otto and Vinalni, but I'm not going to go into too much details here. But if we go back to this dimension-free phenomenon of the log Sobolev constant, then we can ask what are behind this. First of all, you have the ellipticity of the generator, the Laplacian, Rn or half Laplacian. Second, you need the Ricci lower bound, at least in the Riemannian setting. You don't see it that much in Rn because it's a flat model. But actually, in the famous estimate by Beckery and Emery, they prove a gamma-2 lower bound, the Beckery-Emery estimate, and the constant in that Beckery-Emery estimate does depend on the Ricci curvature of your space and its lower bound. Last but not the least, from the explicit form of this inequality, we need the heat kernel and its smoothness, but actually quite beyond the smoothness to prove a log Sobolev inequality. The setting we consider, as Masha explained, are sub-Riemannian manifolds, which most of the above three assumptions would fail. So for completeness, let me still briefly go through the definition and some concrete examples. So as Masha explained, here we consider a sub-Riemannian manifold, a smooth manifold equipped with a sub-bundle, which we call the horizontal distribution, and it satisfies the homogeneous condition. So finitely many Lie bracket, iterative Lie bracket would give you the whole sub-bundle. And this inner product, we call it sub-Riemannian metric. It's equipped on this horizontal distribution edge. And one way to think about this, to visualize this, is the parallel parking. So you are only allowed to move in certain directions, but in the end, you can always arrive at your destination. And this comes from the Chow-Rorschach theorem guaranteed by the homogeneous condition. But from a more analytic point of view, that is, you have a sub-Laplacian, an analog of the Laplace operator, and this operator is hypoelliptic. And this hypoellipticity comes from the homogeneous condition. And as we see from Masha's talk, this hypoellipticity is much weaker than the usual elliptic operator we consider in the Riemannian setting or other cases. Let me briefly give two concrete examples just to remind you, because actually later our results are built upon these two type of examples. So the first one is the three-dimensional Heisenberg group. We already saw in Masha's talk. So this is a three-dimensional non-commutative Lie group, and that's modeled on R3, and it has a one-dimensional center. You can view it as R1. And this non-commutativity comes from the standard symplectic bilinear form from R2 times R2 to R1. And the standard symplectic bilinear form has such an explicit formula. In some other cases, some people also refer to this group as the isotropic Heisenberg group, because this symplectic form, omega 0, is an isotropic symplectic bilinear form. And later we will see a more general examples, which the symplectic form may not have to be isotropic. And here, this symplectic space, here is R2, this symplectic space can be of higher dimension. Just to remind you again, we have a natural sub-Riemannian structure in such a form. So you take three left invariant vector fields, and we have the bracket generating condition like this: x tilde bracket y, x tilde and y tilde bracket gives z. And the horizontal distribution is spanned by x tilde and y tilde. So it has a two-dimensional horizontal space. You have the homogeneous condition, and the sub-Laplacian has such a concrete form. So it's just the sum of the square of x tilde and y tilde, and it's hypoelliptic. And this is the flat model, as Marsha mentioned. The second example is SU2. So 2x2 unitary matrices. We have the Lie algebra spanned by such three polymatrices. Here is the Homanda condition satisfied by SU2. Again, here you have this type of cyclic Lie bracket result. And the horizontal distribution are spanned by x tilde and y tilde. So still two-dimensional horizontal space. And again, we have a very concrete sub-Laplacian, still as a sum of squares, two vector fields. And this is the positively curved model in sub-Riemannian geometry. The reason I go through these two examples again is that actually these two examples are the mostly studied and probably only studied concrete examples for functional inequalities, especially log Sobolev inequalities in the hypoelliptic setting or in the sub-Riemannian setting. While if you want to move forward to a more general cases, say if you just want to drop the group structure, it's not so direct using the techniques available. But let's again describe the problem we want to study here. So given a sub-Riemannian manifold, suppose if you have an analog of Gaussian measure, then we want to prove a log Sobolev inequality of a very similar form as we have seen earlier in the classical case. While on the right-hand side here, you have the horizontal gradient, and this is given according to the sub-Riemannian structure here, sub-Riemannian metric. And also, sometimes we can refer to the right-hand side here, this integral as the Dirichlet form. So if such an inequality holds, then what's more? How does this constant depend on the geometry of the underlying space M? We know the geometry of M can be very messy. And moreover, it's the constant capital C still independent of the dimension, and this is what we hope for. Let me still mention some fundamental difficulties. Marsha gave some in a general perspective, but actually for log Sobolev, it's more difficult to study in some sense. So first of all, for the non-canonical choice of reference measure, we know there are two canonical choice people use the most. That is the Hausdorff measure and the Popp's measure. But why do we need to consider this question? Because when you study the log Sobolev inequality, for the analog of the Gaussian measure, we want to take it as the heat kernel measure. That is, a direct thought would be, okay, I just take the heat kernel for the sub-Laplacian and times some nicely chosen reference measure, and this is my choice of measure. But even if you have the sub-Laplacian in this case, if you take different reference measure, the formula of the heat kernel can be different from each other. Say if you have two different heat kernel formula and then you move on to prove the log Sobolev, and if you have the luck and did prove this inequality, the constant could be different based on your different choice of reference measure. However, even for the reference measure, it's not always explicit in this case. As we know from Marsha's talk, that if your sub-Riemannian manifold has a nice group structure, well, Hausdorff measure and Popp's volume, they are scalar multiple of each other. But if you drop the group structure, this is not clear. For example, if you look at some sub-Riemannian manifold that has a singular set, the simplest case would be the Gaussian plane. There is a singular set, so even if you want to write out the explicit formula for the Pop's volume, it can be quite difficult, even though some people did it, but generally, it still takes you some time and effort to even get the reference measure. And when you move on to solve the heat equation, okay, that's really a lot. Second, the generator sub-Laplacian is not elliptic but hypoelliptic. This would make the analysis more challenging, but how is it related to the log Sobolev? Well, usually, if you want to prove a log Sobolev inequality with respect to some weighted measure, here is the heat kernel measure, then the density for this weighted measure, you do need some nice estimate. And if you take the heat kernel measure here, the usual type of Gaussian estimate will not be enough if you want to prove a log Sobolev here. Even in the simplest non-trivial example, that is the three-dimensional isotropic Heisenberg group, it's quite involving to get such a heat kernel estimate. It is first done by HQ Lee. But if you move to more complicated spaces, you just take kernel group as an example. But from what we know, as far as what we know up to now, I think only 3 examples have been studied in terms of the heat kernel estimate. So if you want to move on to more general cases, and even you consider a sub-Riemannian manifold without group structure, and you want to get such heat kernel estimate, it can be really messy. Third, geometric techniques are not readily available. So as Marsha mentioned, here in the Riemannian case, usually you use the Becquerel-Emery estimate. That is the gamma 2 lower bound. But in our setting, the sub-Riemannian manifold, only the generalized curvature dimension inequality is available, but it only works for a class of manifolds, say step 2. And also, if you want to look at some spaces with singular structure, it cannot be directly applied. And last but not least, function inequalities are more difficult to prove or have to be modified. Still, let me briefly go through some literature. So in terms of the study of log Sobolev inequalities in the sub-Riemannian setting, most of the work has been done in 2 cases. One is the Heisenberg group, and the other is SU2. And for the Heisenberg group case, there are many approaches, and also due to their different choice of the measure, we can take the heat kernel measure or the Gaussian type of measure and so on. There are many different versions of log Sobolev inequality. So here I only listed several papers that are most relevant to our result. So the first one by HQ Lee in 2006 and the second one by Nate Aldridge in 2009, they used the heat kernel estimate approach. So one is for the 3-dimensional isotropic Heisenberg group, and the second did it for more general case for H-type group. And the paper by Herbich and Zaglinski in 2010 used a tensorization argument. The third one by Frank and Leap, their version of log Sobolev inequality is with respect to the Haar measure. And I think their approach is more through a CR geometry type of approach. Moreover, their constant is dimension dependent, even though it's optimal. In 2012, Baudin and Bonifay also proved a version of log-Sobolev inequality based on the generalized curvature dimension inequality, but their choice of the measure is the invariant measure. So in our case, it's the harm measure on the group, and it's not the heat kernel measure. The last one, by Bonifay and Chaffin and Hearing in 2018, and this used a probabilistic approach using the random walk approximation to prove the log-Sobolev inequality. They do get a nice constant. However, their choice of measure is not the heat kernel measure, but another law of some diffusion processes. Here I mentioned above, they are all more related to the isotropic Heisenberg group, three-dimensional or higher dimensional. While in the what's called the non-isotropic case, which I will mention later, only two results are known so far. So Bodegger and Zagalinsky studied a concrete example in that case, but their choice of measure is a Gaussian type of measure. But to go from the Gaussian type of measure to a hypoelliptic heat kernel measure, that's what we aimed for, there's still some long way to go. Also in 2021, Ye Zhang proved a log-Sobolev inequality with respect to the heat kernel measure. However, this approach is more analytic based on the study of the heat kernel in that case. So there's not much information about the constant known if you track their approach directly. So generally, no known results given the constant and its dimension independence property have been known so far. While in the SU2 case, this is proved by Luguiz and Zagalinsky in 2007, even though their statement is written in terms of a more general complex group that has a sub-Riemannian structure. But if you follow the approach directly, you cannot get any information on the constant. It's not easy to track the dependence of the constant on the underlying geometry, and let alone the dimension independence. So what do we need to do? And this is what we did so far. So we considered a class of sub-Riemannian manifolds with nice symmetry, and this is the homogeneous spaces. And here is our main result. Given a homogeneous space M, and let G be a connected Lie group acting transitively on the sub-Riemannian manifold M. Here, G has a left invariant sub-Riemannian structure. And we take, so in this case, in the group setting, you can have the heat kernel measure mu T of G on the group generated by the sub-Laplacian. Here, let us assume there is a hypoelliptic log-Sobolev inequality holds with respect to the heat kernel measure on the acting group G. Then here is what we proved. First of all, we proved that the homogeneous space also has a natural sub-Riemannian structure, this 3 triple, and this is induced by the transitive action of G. So in this case, you can also obtain a hypoelliptic sub-Laplacian, and you can also have the Carnot-Cartesian distance well defined on this homogeneous space M. And this is all induced by the action of G. However, without further assumption, this metric space M can be very different. So for example, M may not have to be a complete metric space under the Carnot-Cartesian distance. For example, we have the Gaussian plane. It's not complete. Second, induced by the action of G, there is a hypoelliptic heat kernel measure mu T of M on the homogeneous space M, such that the heat equation holds. We proved its existence, but later we realized you can also get the uniqueness of this heat kernel measure. However, in this using this approach, you may not get the explicit formula for this heat kernel measure because of the different choice of reference measure. But actually, to prove the Logarithmic inequality, you don't need this explicit formula. Just the uniqueness and the existence will be enough. And this is the push forward of the heat kernel measure on G by the natural map from G to M, which I will explain later. Now, with the existence and uniqueness of this heat kernel measure, then you can define a nicely behaved Dirichlet form on the homogeneous space, and we can show it's closable as well. But last but not the least, this allows us to show a log-Sobolev inequality with respect to the heat kernel measure on M. Moreover, we get this formula for the constant. That is, the log-Sobolev constant on M can be chosen to be the same as the one on G. This equation allows us to track the dependence of the log-Sobolev constant on the geometry of the underlying space M. You see that this constant only depends on the acting group G. So that means if you know how it behaves, the constant behaves on G, then you know how it behaves on M. And here, this constant will be independent of the isotropy subgroup in that case. And altogether, this method will allow us to track the dimension, to study the dimension independence property of the log-Sobolev constant on several homogeneous spaces that have sub-Riemannian structures. Before I move on to concrete examples, let me briefly discuss the proof or the main idea of this proof. This is a quite geometric proof, so we use the homogeneous space characterization theorem. That is, you can always characterize the homogeneous space M as a quotient space, G mod H. Well, here H is a closed subgroup, which up to an isomorphism, you can think about it as the isotropy subgroup for your homogeneous space. And this relation tells us even if you have two homogeneous space, if they have the same transitively acting group, then our method tells you they can have the same log-Sobolev constant, which we will explain in some more concrete examples. And moreover, this characterization theorem says there is a one-to-one correspondence between the H, the closed subgroup, and M. But there are several things to notice here. Since it can be viewed as a quotient group, quotient space, G mod H, so there is a natural quotient map between the group G and this homogeneous space M. And as you see in the earlier talk by Marsha, in some concrete case, the quotient map from G to M, it's a sub-Riemannian submersion. That is, it preserves the sub-Riemannian metric, this quotient map. But here, actually, we don't have to require this quotient map always to be an isometry. Because, for example, you can have the Grecian plane, and where the dimension of the horizontal space M can be different from the dimension of the horizontal space for G. And also, using this method, the dimension of the horizontal space on M can even be different on different points. So that's what we call the rank varying cases. And later I will give some examples. Second, as we know, the homogeneous space M here does not have to be a group for always. Only when the closed subgroup H, your isotropic subgroup, is normal, then you will get a Lie group for M. So later in the rest part of my talk, I will give some examples both for M to be a Lie group and for M to be a non-Lie group. And also I will discuss the case where M has a singular sub-Riemannian structure and when M does not have that. So next, I'm going to provide two types of examples. They are mostly built on Heisenberg group, three-dimensional, and the SU2, because they are the two cases where log Sobolev is known in the sub-Riemannian setting. So the first type of examples are built upon the three-dimensional isotropic Heisenberg group. So in that case, the log Sobolev inequality is already known, proved by HQ Lie. And using a tensorization argument, as Masha mentioned, we can show a log Sobolev inequality on such a product group. Then the type of sub-Riemannian manifold we consider here is a step 2 sub-Riemannian manifold, and the transitively acting group here we take is this product group. Then our earlier general theory tells you for such class of sub-Riemannian manifolds, they all satisfy the log Sobolev inequality with respect to the heat kernel measure. And moreover, for such class of sub-Riemannian manifolds, when they have the same acting group G, their log Sobolev constant can all chosen to be the same as the log Sobolev constant on the three-dimensional isotropic Heisenberg group. So here you actually get rid of the influence of both the dimension and the underlying geometry. The geometry of M can be messy, but for the constant, they are just the same. And moreover, in this concrete case, the log Sobolev constant also has a linear growth in the time t. And therefore, we have the dimension independence. So several examples fall into this category. So the first one is the Grecian plane. It's a two-dimensional space, and we can consider the Grecian operator there. But what's special about this is that it has a singular structure. So from our perspective, actually the Grecian plane can be regarded as a homogeneous space, while the action group here is taken to be the three-dimensional isotropic Heisenberg group. And we prove the log Sobolev inequality. Sorry, it's going there, and we get the same constant as the Heisenberg one. The second type of example is the non-isotropic Heisenberg group. So actually, the non-isotropic Heisenberg group is defined on a finite dimensional symplectic space V. So it can be regarded as this symplectic space times R1, equipped with a non-commutative group law. Well, R1 would give you the center coming from the central extension, and this is obtained from this symplectic bilinear form, omega from V times V to R1. So actually, we are considering a family of Lie groups labeled by this symplectic bilinear form. But the non-isotropic Heisenberg group, we see more. It's of such a form. Here, you have, this is because when your finite dimensional symplectic space is equipped with an inner product structure, then up to isomorphism, your non-isotropic Heisenberg group can always be written as R2n times R1 equipped with such a non-commutative law. While here, you still have a symplectic bilinear form, but it's much simpler. That is, you can sort of diagonalize this symplectic bilinear form. And the influence of the non-isotropic property will appear here as the constant alpha I. So when all alpha i's are the same, that corresponds to the isotropic case. But when they are not, this would correspond to the non-isotropic case. We showed that this non-isotropic Heisenberg group is a homogeneous space under the action of product group, and we proved the log-Sobolev inequality with the same constant as the three-dimensional isotropic Heisenberg group. So here you don't see any influence of this symplectic bilinear form omega. And moreover, you get the dimension independence result. And this is what we did in 2022. And later, this result allows us to extend it to the infinite dimensional setting. So for the time matter, let me only briefly mention the infinite dimensional Heisenberg-like group. We only consider the case when it has a one-dimensional center. But this is an infinite dimensional Lie group modeled on abstract Wiener space. And this is first, this model is first constructed by Marsha and Driver. And it has a natural sub-Riemannian structure, the infinite dimensional type. So you have an analog for the sub-Laplacian, which we call a sub-elliptic operator. However, if you want to prove a log-Sobolev inequality for this sub-elliptic operator, there is some fundamental difficulty. That is, there is no harm measure available in the infinite dimensional setting. But still, using the idea of stochastic quantization, you can get an analog of the heat kernel measure. In this case, that is the law of the Brownian motion. And from there, we studied the property of the Dirichlet form given by this heat kernel measure. We showed its closability, and moreover, we proved the log-Sobolev inequality in this infinite dimensional group. What's interesting is that the constant in the infinite dimensional case can be chosen to be the same as the log-Sobolev inequality constant on the three-dimensional Heisenberg group. So you don't see any influence of either the symplectic bilinear form or the dimension, even though here the dimensions can be regarded to be infinity. In a similar manner, you can look at the extension of non-isotropic Heisenberg group, which we call a Heisenberg-like group. So here, the dimension of the center is greater than 1. But in each direction in your center, you can sort of write it in a very similar form as in the non-isotropic Heisenberg group. We showed that this is a homogeneous space under the action of the product group, and we get the constant. And moreover, we get the compact Heisenberg Neo manifold. We showed that this is also a homogeneous space under the action of the isotropic high-dimensional Heisenberg group. and we get the same constant as the three-dimensional isotropic Heisenberg group. Actually, here, for this class of compact Heisenberg Near manifold, if you take different isotropy subgroup, we know that their topology can be quite different, but our result tells you no matter how different the topologies are, okay, they still have the same log Sobolev constant and they are dimension free. The second type of example is based on SU2. So this can be shown in a similar manner. So if you have a sub-Riemannian manifold under the transitive action of a product of SU2, then you get log Sobolev inequality with the same constant as SU2. Therefore, you get the dimension independence result. And in this case, you have the Hopf vibration and SO3. They both fall into this category and they are step 2. And the last one is SO4. As Mesha mentioned, this is no longer step 2. But still, you can view it as a homogeneous space under the action of SU2 times SU2. You get the log Sobolev together with its constant, the same as the one on SU2. Therefore, you get the dimension-free property. So for further directions, we will look at other groups and other spaces because in our argument, the symmetry, which is induced by the group action, is used heavily. So we would also like to look at this interplay between different symmetries and functional inequalities. And also we want to look at the extension in infinite dimensional settings, but not just functional inequalities. Say if you have other properties, how would this behave under such symmetries? So this is all I want to talk about. Thank you very much.